आ गया तो बता देना. आ गया ना? I have got the message. Yeah.
हाँ सर.
So yeah. So after this, now what we are supposed to do? I think this particular graph also, wherein that viscosity is taken along y-axis and that your n times mu times n times mu by that p, that value is taken along your x-axis. Okay, so that also we have discussed, and how on the basis of this particular nature of the graph we can divide this particular lubrication system into a thin and a hydrodynamic lubrication system. That is what we discussed. Okay, now as far as the performance, as far as the operation of operation performed under the boundary lubrication, yeah, thin lubrication is concerned, in this particular case, what you will notice, as the temperature is going to increase, let's say you have used a liquid lubricant. So in case of your liquid lubrication system, what is going to happen with increase of your temperature? That viscosity has to increase or decrease. Viscosity is going to decrease in case of your liquids, isn't it? Hello? Hello, are you there or not?
Yes, sir.
Yeah. So what I am saying, ki in case of your liquid lubricants, with increase of your temperature, that viscosity is going to decrease. Okay. And also there will be an increase in the heat when the temperature is going to increase. So the heat generated, that will also is going to increase. So what one has to make sure, you have to make sure that what provision you are going to make as far as the entire casing, yeah, what you can say, the outer casing, outer body of your entire bearing. So over that you have to make either that fins are to be provided just to increase the surface area. That is the one arrangement that usually we do. Or else what we can do, we have to make sure that whatever the lube oil that we are going to use, so just make sure that that lube oil is cooled by some means. So in some cases they suggest that you make use of some oil sump from where that lube oil is pumped. Again, after some time, when the temperature of the oil is going to increase, that particular oil with a higher temperature, so that is recirculated to your oil sump, wherein the provision is made to cool it and again it is recirculated back to the bearing. So that kind of thing is done, but again this is something costlier. So as far as possible, by making use of the fins, try to increase the surface area. That is the simplest way to take care of the rise in temperature, increasing temperature of your lube oil. Okay, now after this I want to talk about, yeah, from the discussion that we had till now, it is clear to you that as far as the uses of your hydrodynamic journal bearing are concerned, so we are using this particular hydrodynamic journal bearing whenever we have to support a heavy load and the shaft is rotating at a higher speed. Okay, so some of the applications you can say when there is a heavy load and when there is a the shaft is rotating at a higher speed, so that time we are making use of this hydrodynamic journal bearing. Then in some cases wherein we are going to use that split bearing. Okay, for example, in case of the big ends of your connecting rods, so these are usually fitted with this split type of bearings. Okay, so in that particular case we are making use of this hydrodynamic journal bearing. Then in some cases wherein the some shock load, yeah, vibration ka issue, yeah, some impact loads are there. So in that particular cases also, we are making use of this hydrodynamic journal bearing. Okay. Now, okay. So by now it is clear to you कि though, just a minute, though we say that कि in case of, just a minute, just give me a minute, let me show one small figure, draw a small figure over here. Yeah, so see here now, just a minute. So this outer one, the hatched portion, that is nothing but that is your bearing. Yeah, that is your bush. Okay, that is your bearing. Yeah, that is your bush. And this white color ka ellipse that I am showing, so that is indicating your shaft, or which is also known as your journal. Which is also known as your journal. Okay. Now see here, this particular space. Okay, this particular waist shaped space. So that we are going to fill with the lube oil. Okay. Now it is clear to everyone now as far as that particular shaft is concerned, shaft and the or rather, let me write it, outside diameter of your shaft and the inside diameter of your bearing. Okay, so what type of fit is required? So here we need that clearance type of fit. We need that clearance type of fit. So as a designer, you should know what type of tolerance grade, okay, tolerance grade that we should select as far as this shaft and the inside diameter of your bearing is concerned. So do you have any idea regarding this fits? How I mean the fundamental deviation and the tolerance grade, how to select it? All of you are familiar with the as far as this tolerance is concerned. So we follow two types of system. One is the shaft based system and the another one that is your hole based system. Am I right? Out of this shaft based system and a hole based system, this hole based system is more popular. Am I right or not? In case of your hole based system, let us say you have say I'm taking a random example. Let's say I have a diameter of shaft, say a 90 millimeter. So, and in that particular case, I need to specify the tolerance on that of your bearing, inside diameter of your bearing and that shaft ka diameter. So, as if that particular, this particular diameter is your inner feature, yeah, inner dimension. So I will treat it as whole, right? And this particular diameter, this is your external feature, and hence it is treated as the shaft. Okay, so here when we are going to follow that hole based system, so as far as the hole based system and the fundamental deviation for that hole is concerned, in a hole based system we use letter capital H, then it is followed by one number. It may be 7, it may be 8. We are using the tolerance grade total 18 tolerance grade we are using, starting from 0, 1, 0, 0, 1, 2, 3, up to what? Up to 16. So 1 to 16, these are the 16 number, and that 0, 1 and 0, 0. So in all, we have the 18 tolerance grades. And the fundamental deviation that we are going to denote with this alphabets. Okay, the capital alphabets we are using for whole, and the small alphabets we use for the sharp. So let's say I have used that H7. So H7 is the tolerance value for your that hole, I mean the inside diameter of your bearing, and then I have to put that slash, and let's say D7, yeah, E7. Suppose from this particular letter, small d or small e, it is clear that this particular combination is giving me what? Is giving me that clearance type of fit. So why I am saying it? The reason behind it is that here, just a minute, let me show you. Are you understanding what I am talking? Hello?
Yes, sir.
Yes, sir.
Just give me a minute. Let me open this. I'm talking about this. Yeah. So in case of your, as I was telling to you just now, in case of your whole base system, this is your capital H. Okay, and you can see over here that any letter from that small a up to that small g, so that is giving you what? That is going to give you that clearance fit only. So usually what we do, we are using that H7, E7, yeah, H8, D8. So these combinations we are using. I will show you from where you will get this particular things. Just a minute. Here in the PSG only, they have given you. Just a minute. Right now that PSG is visible on your screen. Am I right?
Yes.
Yes, sir.
Yeah. So see here, here this is page number 3.4. Page number 3.4, and in this, on this page number 3.4, you can see over here, this is your loose running fit. So in case of your loose running fit, irrespective of the diameter of your hole, yeah, diameter of your shaft, that H8 D8, that is going to give you that loose running fit. Similarly, that H8 D9, that is going to give you normal loose running fit. Then H9 D9, that is giving you that coarse loose running fit. Okay. So at the beginning, you have to specify what type of fit you are going to use. So normally that loose running fit we prefer. So in that loose running fit, again there are three subtypes: fine, normal, and the coarse. Okay, so anything is okay. So you can take irrespective of the diameter. I mean, 80 suppose is the diameter of your shaft, yeah, diameter, inside diameter of your bearing. So in that particular case, you can specify the dimensions like this: 80 H8 D8, H8 D8. Some I usually put the slash between this. Here it is not been shown, but normally as per the IS conventions, it is a common practice to separate the tolerances for your hole and the shaft with the help of this slash. Okay, I hope it is clear. So H8 D8, usually the students didn't understand why here we are taking that H8 D8, yeah, H7 F7, H8 E8. Why these letters? Why this particular fundamental deviations for your hole and shaft are being taken? So for that, already I have shown you this particular thing that you will get on page number 3.4 of your PhD. Now, this particular slide, this is talking about that that hydrodynamic action. Already I have spoken about that. Okay, Now, in this particular figure, just those who have not attended my previous lecture, so for them, let me tell you, here in this particular figure, what this particular figure is showing, this is the radial load which is coming over here, that has been shown. So which is your load W, and the outer one, that is your bush. This particular dots are showing the oil, and the innermost circle, this one, so that is showing you what? That is showing you this one, that is showing you the shaft journal. And here in this particular waste shift lube oil waste shift region, that oil pressure gets generated once that shaft starts rotating. Okay, now we have to discuss about the various terms associated with this hydrodynamic bearing. As far as the first term is concerned, so just a minute. Yeah, so the first term is your diametral clearance. So with respect to this particular figure, I will show you. Now see here. Now suppose the diameter of your the shaft is, say, suppose 80, and the inside diameter of this particular hole is, say, suppose 81. So here both these numbers are talking what? Both these numbers are giving you the diameter of that shaft and the diameter of that of your hole. So 81 minus that 80, so that is equal to your 1 millimeter. So what this 1 millimeter is? That 1 millimeter is nothing but that is your diametral clearance. So difference in the diameters of your hole and the diameter of your shaft, that is nothing but that is called as your diametral clearance. So if capital C is the notation that we are using for denoting that diametral clearance, and that CR, capital letter C with suffix R, is the notation that we are using, let's say, for the radial clearance. So then it is clear that diametral clearance is equal to what? Diametral clearance is equal to your 2 times the radial clearance. Okay, so CR is the notation that we are using for denoting your radial clearance, and that capital C is the notation that we are using for this thing. Capital C for diametral clearance and CR for the radial clearance. Anyway, now regarding that bearing pressure, whatever the pressure that has been generated in your lube oil, so how you are going to calculate it? Suppose capital P is the notation that we are using for that bearing pressure, then that is calculated using this particular formula, that capital P is equal to that W upon that L into D. Why I am using this particular relation, let me clarify. See here, this is your this is, say, your journal, and on it, let's say, this is your load W is coming over here. Now this diameter is your capital D, and length is, say, suppose capital L. Length is your capital L. Now in this particular case, suppose this is your capital D diameter and this is the length. So in that particular case, this rectangular area will be your L times D. Do you agree or not? So for that reason, we are going to calculate that pressure by using this particular relation, that is W upon L into D. Earlier also we have talked about it. I hope it is clear. Anyone is having any doubt here? Hello?
No, sir.
Okay. Then after that, the next term that I want to talk with you, that is regarding the eccentricity. So from this particular figure, you will understand what is that eccentricity. Suppose this is the center. What is this? This point is nothing but that is the center of your shaft, let's say, and let's say this is the another center, which is the center of your that bearing. Okay, center of that bearing. Now this particular distance, that is nothing but that is called as your eccentricity. That is known as your eccentricity. Am I clear, bachcha log?
Yes, sir.
Yes.
Yeah. So if you have to express that particular eccentricity, now the minimum eccentricity, this particular formula is talking about what? This particular formula is talking about that minimum eccentricity. Now how to calculate that minimum eccentricity? Suppose H naught is the minimum film thickness. To avoid that metal to metal contact, let's say H naught is your minimum film thickness and capital C is your diametral clearance. So in that particular case, that eccentricity small e you can calculate by taking a difference of that radial clearance and that minimum film thickness. Are you understanding? And the minimum film thickness value, in order to avoid that metal to metal contact in case of your hydrodynamic journal bearing, that minimum film thickness we have to ensure that it is more than 0.001 times the diameter of your shaft. Okay, to avoid that metal to metal contact, the minimum value of your film thickness that should be greater than 0.001 times the diameter of your shaft. Okay, then the next term involved over here, that is your eccentricity factor, or it is also known as the attitude. Okay, so as far as that eccentricity factor is concerned, so it has been denoted with the notation epsilon. You can see here it has been denoted with the notation epsilon, and that epsilon, yeah, eccentricity factor, that is the ratio of 2 times the eccentricity divided by your, yeah, eccentricity upon your radial clearance. That eccentricity factor, that is nothing but that is a ratio of what? That is a ratio of your eccentricity upon radial clearance. Okay, so if in place of the radial clear, if you are writing that radial clearance in terms of the diametral clearance, so in that particular case you will get this particular relation for your epsilon, yeah, for your that eccentricity factor. Yeah. Now after this, the next term which is important here, that is the attitude angle. Let us say let us say ki here you are getting that minimum film thickness. Here you are getting the minimum film thickness to avoid your metal to metal contact. Okay, so this is your H naught ka value. Now let's say so along this vertical, what we are getting? We are getting that external load W. Okay. Now what I'm saying, we have to now locate the position of your minimum film thickness. So for locating the position of your minimum film thickness, we are going to take help of the direction of the load, which is coming on your shaft. Okay. Now, what happened here? Just a minute. So let's say now I want you to focus over here. Can we say that this is your minimum film thickness? Okay, suppose this is the minimum film thickness H naught for avoiding your metal to metal contact, and right now we are talking about that attitude angle. Okay, so as far as that attitude angle is concerned, so it is nothing but it is the angle which is needed for locating the position of your minimum film thickness with respect to this direction of load. So this is your direction of the load. Along this direction your external load is acting, and along this dotted line which I have shown here over this particular line we are getting that minimum film thickness. And now this particular included your angle, so that is nothing but that is the angle which is which will help us to locate that minimum film thickness with respect to the position of minimum film thickness with respect to that direction of the load, and that angle is called as your that attitude angle. I hope I am clear. Anyone is having any doubt over here? Bachcha log? Hello.
So could you repeat it again?
See what I was talking about the attitude angle. Okay, now in this particular figure what I have shown, this outer two white ellipse, what they indicate, what these outer two ellipses are indicating? Can anyone tell me? This outer two ellipse, these are nothing but that is our bush, yeah, bearing, right? Now this particular circle or the ellipse which is shown at the center, so that is nothing but that is your shaft. Now in this particular figure what I have shown that now that shaft is in motion, that is rotating. Right now you can see that the space between there is a clearance space between your surface of the shaft and the inside diameter of your bearing. So right now this is the minimum film thickness that we are getting when that particular shaft is in motion, when it is in a rotational motion. Okay, now in this particular rotational motion we have to find out what is the minimum film thickness so that we can avoid that metal to metal contact. In case of your hydrodynamic journal bearing, what we don't expect that direct metal to metal contact. Okay, so in such cases this is the minimum film thickness that we need. Now this minimum film thickness, this particular line that has been extended till up to the center of your journal, let's say, and over this particular journal, yeah, on this particular shaft the radial load, external radial load coming, that has been shown by this particular arrow. And now the included angle between the external load and this particular line along which we are getting that minimum film thickness. So that angle we have to measure, and that angle will help you. That angle will give you the direction of minimum film thickness, direction of minimum film thickness. But this we are measuring with respect to what? With respect to the external load, yeah, radial load which is coming on your shaft, and this angle we call as the attitude angle. I hope now I am clear. Bachalo?
Yes, sir.
Yeah. Now the another term, yeah, as far as this your hydrodynamic journal bearings are concerned, so here that L by D ratio matters a lot. Okay, so there are three possibilities. L is the length of your bush, yeah, length of your bearing, and capital D, that is the diameter of your journal, yeah, inside diameter of your bearing. Now that L by D ratio, there are three possibilities. Either it is equal to 1, yeah, it is greater than 1, yeah, it is less than 1. So when it is equal to 1, so that time it is known as the square bearing. It is known as the square bearing. When it is greater than 1, when it is greater than 1, so that time it is known as the long journal bearing. And when it is less than 1, so that time it is known as the short bearing. It is known as the short bearing. Am I clear? Now, as far as possible in our design, we are going to take that square bearing. Whenever we are going to solve the problem, so that time we are going to take that L by D ratio as 1. If that L by D ratio is less than 1, so in that case, as I said, it is known as the short bearing. So in this particular case, with that L by D ratio less than 1, you will have a problem of the heat dissipation. Heat dissipation is better, but the load carrying capacity, that will be the problem. Okay, so in case of that L by D ratio is greater than 1, so in that case unnecessarily there will be a wastage of the lot of lube oil. That is the problem. So just to make sure that we are making the optimum use of that lube oil, we have to take that L by D ratio equal to 1. Is this clear? But chalo.
Yes, sir.
Yeah.
Yes, sir.
Yeah, thank you. Now, the another important term as far as the design of your hydrodynamic bearing is concerned, so there is one parameter which is called as the bearing characteristic number, and that has been called as the Sommerfeld number. That Sommerfeld number is given by this particular formulae, wherein we say that we denote that Sommerfeld number with the notation capital S, and it is equal to that Z dash into N dash divided by P. This particular number, that is known as your bearing characteristic number, and into that capital D upon C whole bracket ka square. Okay, now here in this bearing characteristic number, we take the value of that Z dash in in actual practice, the value of your Z, that is the absolute viscosity, that is given to us in centipoise. In fact, in the PhD, that viscosity is expressed in the centipoise. Okay, now here we are using this particular viscosity. We are using in kgf centimeter per second square. So we have to see that how we are going to convert that viscosity from centipoise to that kgf centimeter per second square. Okay, so for that what we are going to do, if I need that particular viscosity Z dash in kgf centimeter per second square, so in that particular case, that viscosity which is given to me in centipoise, that is to be divided by 9.81 into 10 to the power minus 7, sorry, 10 to the power plus 7. So that will give us the value of that particular dynamic viscosity in kg of centimeter per second square. Okay. Now here we are using that n dash. Here that notation small n dash is used. Now what is that n dash? So that is nothing but that is the speed of your what you can say, speed of your shaft, yes, speed of your journal in revolutions per second, So that means whatever the RPM is given to you, that has to be divided by 60, and that number you are going to enter over here. Then this number capital P, which is appearing here in the denominator, that is nothing but that is your bearing pressure. That is nothing but that is your bearing pressure, which is taken in pascals in SI unit. Okay. So as I told you, this entire number, that Z dash into N dash, whole thing divided by that P, that is called as bearing characteristic number. Also in some books they call it as the bearing modulus. They call it as the bearing modulus. Okay. Okay. Then regarding that attitude angle, whatever we discussed earlier, the same thing. Yeah. So whatever the external load which is coming on your shaft, let's say you are taking its X component, Y component. So by taking that X component and Y component, you can find out that attitude angle in terms of this components of the external load. Suppose Wx and Wy, these are your X and Y component. Here that X component, Y component, which I have shown over here. So that I hope you will understand. Here I am assuming that this is your along this side. This is my X axis and this is my Y axis I have taken. So for that reason, this is I have taken Wy and this is I have taken Wx. So how you are going to fix up your reference coordinate frame? So that is important as far as the values of your X and Y components are concerned. Okay. So tan of your phi, that is equal to your Wy by Wx. यहाँ तक clear हो गया क्या? Anyone is having any doubt?
No, sir.
Yeah. So as I told you just now regarding that L by D ratio, in the oral examination or in your MCQ exam, sometimes a question you can expect about that. That is what is the importance of that L by D ratio as far as the design of your hydrodynamic journal bearing is concerned. So that bearing, we can say that as far bearing performance is affected by that L by D ratio. So when that L by D ratio is going to increase, what we have written? We have written that bearing pressure, pressure is equal to your W upon L times D. Now when that L by D ratio is more, so in that particular case, ultimately what you can say as that L by D ratio is going to increase, that intensity of your pressure, intensity of this particular pressure, that is also going to increase. Okay. Now for that reason, what we can say that this L by D ratio greater than 1, so that means it is treated as your long bearing. It is treated as a long bearing. Just now I gave you the classification: long bearing, short bearing, and the square bearing. So when your L by D ratio is greater than 1, so that time the load carrying capacity of your bearing, that is more. Now this particular thing that you can say in comparison to your short bearing, wherein L by D ratio is less than 1. L by D ratio is less than 1. So in comparison to your short bearing, you can say that long bearing is having the more load carrying capacity. Okay. But though this is true, here in this particular case, as I told you earlier, you need more supply of the lube oil. So what you can say, when the supply of fluid, supply of lube oil, you are going to increase. So it is going to increase the side flow. I mean, key from the ends, Just a minute. Suppose this is your that say bush. So from this end, there will be a lot of side flow of your lube oil. Okay, but definitely that will help us for improving the heat dissipation, no doubt. When the amount of oil that you are using is more, so in that particular case, that heat dissipation, that will be more, that heat dissipation capacity gets improved. That is what we can say. But again, as I told you earlier, when that L by D ratio, when L by D ratio is greater than 1, so that time the chances of having that metal to metal contact at this ends, chances of getting that metal to metal contact at the end are more. Okay. Also, sometimes when that L by D ratio is greater than 1, so there is a possibility that shaft may get deflected when the load is going to be increased. When the load is increased, so in that particular case, sometimes you may experience the deflection of your shaft. So that deflection is again one sort of failure only. Okay, that deflection ka value should not increase beyond a specified limit. So again, that deflection is also not desirable. So that these are the issues with your long journal bearing. On the other hand, when your shaft and bearing are perfectly aligned, so in that particular case, your shaft deflection is within the limit, and that what you can say, the cooling of your lubricant is also not required. So in for all those cases, what we want that as far as possible, that L by D ratio should be equal to 1, and hence we prefer that L by D ratio as 1. Okay. Now, apart from this, as far as the formulas are concerned, for just a minute, for right now, I talked about that heat generated. Can you see this thing? My PSG I have shared with you. Is it visible to you? Chalo.
Yes, sir.
Just a minute. Just give me a minute. Let me show you 2-3 formulas I want to show you. Yeah, I'm talking about this particular formula. See here they have given you the relation for calculation of the heat generated. Okay, so heat generated, that depends on the coefficient of friction. It depends on the radial load, and it depends on the velocity. See that load का unit is your Newton and velocity ka unit is your meter per second. Okay, so that Newton meter per second, so that Newton meter, that is your joule per second. Okay, so which is nothing but that is your heat generated, but here that heat is generated due to that of your friction. Heat is generated due to your friction, and hence we are going to multiply that W and the velocity by that mu. Okay, and now when you are calculating as far as the performance of your hydrodynamic journal bearing is concerned, so you have to make sure that there is a whatever the heat is generated, the entire amount of heat has to be dissipated. Okay, so heat generated we are going to calculate using this particular relation, and that heat dissipated, that we are going to calculate either using this particular relation, or else we can use that formula HD is equal to that small h into surface area into your delta T, wherein that small h is nothing but that is your convection coefficient. Okay, and that as is your surface area of your bearing, and that delta T is nothing but that is the difference between that of your bearing temperature and that of your ambient temperature, at atmospheric temperature. Okay, so most of the time that if that value of your small h, that is the convective coefficient, suppose it is not given, so in that particular case we are going to assume this particular value between 20 to 25 watt per meter square per degree centigrade. Okay, I'm saying ki this particular number you can use only when that value of your h, small h is missing. So in that particular case only you are going to use this particular relation. Otherwise, if they have given you any other value in the problem, so accordingly you use that particular value. Okay. Now regarding that of your that velocity, again velocity you can calculate by using this relation. V is equal to your pi d n upon 60. Here d is the diameter of your journal, n is the speed. Okay, then that heat dissipated, that is equal to your h into as into delta T. That is what I told you. Now this is what I didn't talk, how to calculate that surface area. As far as the surface area of your bearing is concerned, so this is the empirical relation. You will ask me how this particular relation been written. So this is basically an empirical relation for calculating your surface area of bearing. Okay, 25 times L into D. Okay, and also if this atmospheric temperature, ambient temperature is not given, so in that particular case you can take it 28 to 30 degree centigrade. Okay, if it is not given. Okay, if it is not given. Okay, so this is all about your hydrodynamic journal bearing. Now after this I'm going to talk about the design procedure. So anyone is having any doubt, please unmute and you ask me. Otherwise I will start with the design procedure of your hydrodynamic journal bearing. I mean, what are the various steps that we are going to follow as far as this design of your this thing is concerned. What design of your hydrodynamic journal bearing is concerned. So what are the various steps? What particular data is given to you in the problem? If you remember, when we done the design of your various gears, so that time also I explained you what particular data is given to you and how to proceed. What are the various steps that we supposed to follow? Anyone is having any doubt whatever we discussed till now? If not, then I will go ahead. बच्चा लोग
No, sir.
Yes.
No, sir.
Okay, 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 okay. See, the first step, if that L by D ratio is not given in the problem, they will give you the amount of load to be supported, okay, and the speed of rotation. Now, based on that particular information, the very first thing that I will do, that is, I'm going to decide that L by D ratio. I'm going to decide that L by D ratio. So already I talked about that. And if L by D ratio is not suggested in the problem, so in that case, I'm going to assume that L by D as 1. Now, when we are going to assume that L by D as 1, then the next thing, that is, we have to get the diameter of the shaft. Now, for getting the diameter of the shaft, what we are going to do, we are going to use this particular relation. That is, that pressure is equal to your W upon L into D. Again, sometimes this value of the pressure is not given in the problem. If this pressure ka value is not given, so in that particular case, I am going to assume the value of the pressure as 1.5 or 1.6 megapascal. If the value of this pressure is not given, so in that case, what I'm saying, you can take it between 1.5 to 1.6 megapascal. Again, this you need to assume only if that pressure is not given. Okay. Now, see here, that pressure we have, let's say, that W radial load coming on your shaft, that is known to us, and L by D ratio we have assumed. So that means here in the denominator you can write in terms of the diameter only, and after reshuffling the terms, you will get the value of that diameter. You will get the value of that diameter of the shaft, isn't it? And once you get the diameter of the shaft, then this particular calculated value, that will be in the fraction. Okay. Now, this value we need to round up to the whole number. You can take it in the multiples of 5, or you can take it in the, as the even number. And then for that particular shaft, next thing that you are going to do is, you are going to decide the tolerance ka value for that of your shaft and the hole, which I told you just now, that is H8 D8, yeah, H7 E7, something like that, H7 F7, like that. Okay, so this we are going to do. Now, when you are selecting that particular thing, now see here, what I told you at the beginning, that pressure, W ka value, that will be given to you. Okay, this P bearing pressure may be given, may not be given. So if not given, what number we have to assume, that I told you. And then from that particular thing, what you are going to do, you are going to, after knowing that pressure, you are going to calculate, you are going to assume that L by D ratio, and from here you are going to determine the value of D. After calculating this particular D ka value, what I told you, you have to decide the tolerance value on that shaft and that of your bearing, and find out the actual dimensions of your shaft and that of your bearing. Now, why we have to decide those particular dimensions? Because if you remember, I talked about that of your diametral clearance, that capital C is your diametral clearance. Yeah, that CR, capital C suffix R, that is your radial clearance. Okay, so these are the values. So we have to decide this diametral clearance, yeah, radial clearance, and for that we need the dimensions of your that hole and that of your shaft. Okay, so for that purpose we are doing this particular exercise. Am I clear? Now, once that has been known to you, then the next thing that you are doing, that is, you are going to calculate that bearing characteristic number. Already I told you about that Z dash into your N dash upon that capital P, which is nothing but that is your bearing characteristic number, that you are going to calculate. Then that clearance ratio we are going to calculate. Then we are going to decide, based on that Petrov's equation, you are going to calculate that coefficient of friction. This particular thing that you will get based on that Petrov's equation, and once that coefficient of friction is known to you, then that mu into W into V, that is nothing but that is your heat generated. That is your Bachalo? Hello, students, are you there?
Yes,
Student?
sir.
Yeah.
Yes,
No,
sir.
no, no. Yeah. What happened in the other lab? Rohit sir is sitting and he told me that he lost the connectivity. So for that reason, and I was not getting any response. So from your side, so that is the reason I took pause and asked. Anyway, so after that calculation of your heat generation, as I told you, we have to establish here the thermal equilibrium. So for that reason, we have to calculate that heat dissipated, and then based on that rising temperature delta T, you need to write a comment. You need to write the comment regarding the supply of oil or how you are going to cool that particular oil. So regarding all those things, we need to write the comments. So for that, you are not going to make any, those design aspects, how to take care of that particular surface area and all. So that we are not going to, only we are going to calculate that surface area by using that empirical relation which I told you, which is that 25 times L into D. Okay, and then at the end, what we are going to do, we are going to calculate that frictional power loss, then the maximum pressure, that's how much quantity of your oil is needed, then the quantity of the oil, then the supply pressure, flow rate of your oil. So all those things we are going to decide after that. Okay, is it clear to you, Bachalo?
Yes, sir.
Okay, so we will stop here, and in the next lecture I will start with the this thing. What I will stop with, sorry, I will start with the actual design problem. Okay, just give me a minute. Let me take your attendance just a minute.